Today on The Future of Everything, the future of fresh water. Along with air, I guess I'm being Captain Obvious here, water is probably the most basic and the most important natural resource. We drink it, we clean with it, we grow our plants with it, we grow the plants that we feed livestock with it, and we use it in all kinds of industrial processes. Many of these uses depend on fresh water. Now, again, Captain Obvious will tell you that fresh water comes from the rain that lands in lakes. It also comes from snow and ice that provides spring and other season river flows. And it comes from groundwater, of course. There's a lot of water on Earth, but according to the internet, only 2.5% or so is fresh water. The rest is basically salt water. So if you want to increase the water supply or redistribute the location of usable fresh water, you need to consider desalination, the process of removing salt and presumably other things from salt water to make it fresh. Whatever your process for desalination, it can also not be too energy intensive because we have other challenges with climate change and increasing appetite for energy worldwide that really put a cap on how much energy you can spend on your water. And there are many other challenges as witnessed by the problems that we saw with drinking water in Flint, Michigan over the last few years and others. Professor Meagan Mauter is a professor of civil and environmental engineering, chemical engineering, and a fellow at the Woods Institute for the Environment at Stanford. Her lab works to provide technologies for sustainable water supply by working on desalination, methods for understanding the energy costs for desalination, and translating all of this into better water policies, including for California, pretty big state. Meagan, you've written about the circular water economy. What's the circular water economy?
Yeah, well, let me start out, Russ, by telling you what the linear water economy is. And basically, in the 20th century, we've built this very wonderful water system that takes fresh water sources, it treats it to the level that we need to treat it, and then we use it, somewhat inefficiently often, and discharge it back into the environment. And again, that system has protected us from diseases like cholera. It's allowed us to build large urban cities and basically sustain a way of life for a full century. The issue is that today we're facing these extra challenges, things like climate change, increased urbanization and really high density urbanization, aging infrastructure. So all those sewer systems and drinking water distribution systems that we built 100 years ago are starting to fail.
Yes, I'm constantly being told I have roots in my pipes out of my house and that I have to pay a lot of money for somebody to get rid of those roots.
That's right. So we are sort of faced with this question of how do we adapt this existing system and make it more resilient in the face of all these extra challenges? And one of the ways to do that is to stop thinking about wastewater as a waste and to start thinking about it as a resource. If we're going to tap both water that we've already used, as well as other non-traditional water sources, we really need a whole suite of new treatment technologies. Mm-hmm. And that's where desalination, and particularly membrane-based separations, plays a major role.
Now, what about circular? You promised you would get me to circular.
Yeah. So a circular water economy is really one in which we replace that linear economy, and we are tapping wastewater as a new water source.
Okay, so for somebody who would be just listening, what about the fact that when we do use water, even with the linear pipeline, it winds up eventually being dumped somewhere where it can turn into clouds, rain on us, and replenish in that sense of a circle? Why is that not like the whole answer?
Yeah. So you're right. There's a big water cycle. We learned about it in second grade, right? What engineered systems do is collapse that really long water cycle into something that's much, much shorter. So we're basically making the circle much smaller. I'll say that, actually a lot of our quote unquote linear system involves an awful lot of kind of unintentional or de facto water reuse. But that doesn't always protect human health and the environment in the way that we might hope. And so by employing engineered systems to make that sort of circle tighter, we can both protect human health, protect the environment, and in many cases save an awful lot of cost and energy, because instead of looking broadly for new sources, we're using this wastewater as a resource. And so one of the big advantages of that is we don't actually have to transport that water very far.
Right.
And
Right.
it turns out that about 80% of the energy intensity in supplying water is consumed in water transport.
Great. So, okay. So thank you for that introduction. And I have so many questions. So just to get a little bit nerdy at the beginning of our chat, tell me about desalination as a technology. Like, how does it happen? Because it seems almost like magic. Is it like distilling? Just for people who haven't thought about this, what do you have to do to water? And I know you've done primary research, you're a chemical engineering faculty member. What do you have to do to get salt and other things out of water, technically?
So, right, it comes down to overcoming the sort of thermodynamic energy penalty associated with separating an ion from water, or the delta G of mixing. And in order to do that, you need some energy input. The thermodynamic minimum is somewhere around 1.1 kilowatt hours per cubic meter.
So we're talking energy requiring from the start. There's no way this is going to not be expensive with respect, or at least cost something with respect to energy.
That's right. So thermodynamics tells you that for 50% water recovery from seawater, your minimum energy input is 1.1 kilowatt hours per meter cubed of water produced. Now, the question is, how do you get there? Right? How do you actually perform that separation? And there's many different approaches. Historically, we use thermal approaches. More recently, we rely almost entirely on membrane-based separations, where you have a membrane that is permeable to water, but not permeable to salt, and often also not permeable to other organics in our wastewater or in sort of the water that we're trying to treat. And so that semi-permeable membrane, you're applying a hydraulic pressure in excess of the osmotic pressure difference across the membrane, or the difference in salinity between the pure water permeate, or the freshwater permeate, and the saltwater feed. And so we can use hydraulic pressure coupled with the semi-permeable membrane to produce clean water that's drinkable.
And that is, I was going to say, that is potable. So my very brief summary is under very large pressure through a very specially created, when you say membrane, it's basically like a filter, but it's an amazing filter because water and ions are extremely small. They're also charged in the case of the ions. And by putting that pressure on it, you can get the water to go through, not the ions, and you have beautiful drinking water on the other side. Great. And are we anywhere near that theoretical? You gave some numbers about per meter squared how much energy is required. And I know, of course, you can probably spend more than that. How close are we to making it as efficient as theoretically possible?
Yeah, so using a reverse osmosis process, we're at about 2 times the thermodynamic limit, which is really good.
Yeah.
As far as industrial separation processes go, that's about as good as it gets. And so that forces us to ask really interesting questions about where is there more energy savings? There is definitely more energy savings in opportunities in the pre-treatment application. So before you get to the reverse osmosis step, you have to clean out a lot of the sort of organics, the bacteria, et cetera.
Right. Make sure that salt is your main problem and not other unspeakables.
That's right. And then I think it also really comes down to how do we transport water and how do we manage water? And to the extent that you can avoid doing desalination, you inherently save energy. So water conservation, water efficiency, using lower salinity feed streams as opposed to seawater are all opportunities to sort of more efficiently design and operate your system, rather than trying to just make the reverse osmosis step, which is the most energy intensive step, but again, is so close to the thermodynamic minimum that your return on investment for extra R&D activity might not be that high.
This is the future of everything. I'm Russ Altman. I'm speaking with Professor Meagan Mauter about desalination technologies. And I wanted to ask, you mentioned it earlier in your comments, I think you called it non-traditional sources or perhaps unusual sources of water. What do you mean by that? I know you've written about brine, which I always think of as something that like we do with our cured meats. But tell me a little bit about the kinds of untapped, so to speak, water sources that you get excited about.
Yeah. So again, as we face sort of water scarcity, we're going to start looking for other water sources. And if you are a coastal city in California, the sea looks really attractive. People are building seawater desalination facilities. There's a large operating one in Carlsbad that supplies San Diego with about 20% of its water supply. And there's 10 or so desalination plants around the state of California. If you don't live on the ocean, your options for augmenting water supply are a little bit more limited.
Yeah.
So you're starting to think about brackish groundwater. We have tremendous quantities of semi-saline groundwater that if we're going to use as a water source, we would also need to desalinate.
And how does that compare in its salinity to the ocean?
Yeah, so usually brackish water we say is somewhere between 1,000 and 10,000 parts per million TDS, total dissolved solids, whereas the ocean is about 35,000 parts per million TDS. So it's about a third as saline as the ocean is, third to a quarter. So brackish water is one really obvious inland source. But there are many, many others. And the most obvious one is actually the wastewater that we generate on a daily basis. So it's a very, very drought resilient source because we just kind of keep reusing it in this ever and ever tighter circle. Now, you can't recover 100%, but you can recover a pretty substantive fraction. If you are not a municipality and you're instead an industrial operator, or you are, an agricultural user, you also are generating wastewater. Not that we don't think about those industries as generating much wastewater, but they really do.
Yeah.
So here in California, there's a lot of tile drainage that gets generated that contains a lot of salts.
What was that word? Did you say tile?
Tile drainage.
What is that?
Right. Yeah. So when you irrigate, especially in a place where A, there's a lot of clay soil, and B, there is salt buildup in your soil, you tend to over irrigate and leach some of that irrigation water, and that irrigation drainage then gets discharged into the environment.
Yeah.
So that's not only an environmental issue. So Kesterson Reservoir, for instance, is plagued by selenium issues, or has been for the past 30 years. But also it's an opportunity to think about augmenting irrigation water supplies if you could remove the contaminants of concern, particularly sodium chloride, but also selenium compounds and boron from that tile drainage.
So this is interesting because you've said that, based on where you are at the coast, inland, desert, mountain, there might be other opportunities. There are other opportunities for gathering water, either from natural or from reused sources. But that suggests to me that there's going to be like a hodgepodge solution. And is that where we're headed? Like that it's not going to be a big water utility that looks like with a lot of smokestacks and tanks and stuff, but that it might be a very different look in different regions. Is that the first of all? And the second thing that it makes me think is we might have parallel supplies of water, and we haven't touched upon that. But right now, the water that we garden with, the water that we flush, the water that we drink, it's the same water. So I guess two questions. First is, are we looking at a very different kind of water infrastructure if your visions for desalination play out?
Yeah. So water supply portfolios are more resilient when they're more diverse, because drought can hit surface water sources. It doesn't affect groundwater in the same way, or at least at the same temporal scale. So we really want to diversify these supply portfolios. The other thing that we want to do is we want to, and one way to find really resilient sources is we want to use local sources. Unlike electricity, which is actually a pretty good model for where water is going, unlike electricity, it's really expensive to transport water. like an electron kind of goes across
Right.
wires, and yes, it's expensive to build transmission infrastructure, and yes, you have losses, but like you don't have anywhere near the losses or the expense, the continuous expense in
Yeah.
electricity transmission as you do in water transmission. So you're never going to see a national water grid for that reason. Um,
Ah,
Solutions are always going to be hyper local. And one of our hypotheses is that um, getting even more local than the municipality, getting down to kind of the community scale or the block scale or even the building scale, is a more cost-effective and energy efficient route to supplying that water than it is to think about, or at least some combination of small scale hybridized with centralized systems is a more efficient solution for building that resiliency into the water grid.
so okay, so just to make sure I heard that right, you said maybe not the municipality level, but even all the way down to the home. So you're imagining that in my home, I might have a much bigger kind of set of appliances that are both creating clean water and maybe recollecting and recycling that clean water. Right now it's basically, it comes in and it gets flushed or it goes down, or my wife adds it to our garden in huge volumes every year. But I just want to make sure, is that what you're thinking? So is it possible that I'll have some kind of water appliances?
Treatment appliance. Yeah. There actually is one on the market today. I have no association with it, so this is not an endorsement, but there's something called Hydroloop that's out of it's a Dutch company that's kind of grown out of a research project in the Netherlands with Wetsus and a couple of other companies. But it's a good example of, I think, the future. This is the future of everything.
Right.
So, I want to share with you what I think the future is. The future of like water treatment appliances.
What does their product do? Like, what's the input? What's the output?
You have a choice. You can buy the potable reuse option, which takes water and lets you drink it, or the non-potable reuse option, which lets your wife irrigate with it. So there are several other options in between. The honest truth is that we are much more likely to see this at sort of the building scale or the industrial scale early on, but there isn't any reason why in the future we wouldn't also see that at the household scale. And I would just say that it raises some really interesting research questions around how you design and operate a hybrid system, which is a system in which centralized water distribution is paired with local reuse.
Right. This is the future of everything. I'm Russ Altman. More with our guest, Professor Meagan Mauter, next on Sirius XM. Welcome back to the future of everything. I'm Russ Altman. I'm speaking with Meagan Mauter, and we're talking about water, desalination, and related issues. And one of the things I know you've written about, Meagan, is about air and air emissions and how they impact your task of making sure that the water supply is clean and cleanable. That's, I guess, maybe an obvious connection, but could you flesh it out for us? Why does a water person start worrying about air?
Yeah, so earlier we had spoken a little bit about the energy intensity of water treatment. And it turns out that when you are consuming energy or chemicals to produce clean water, you are also polluting the air. And so it creates this very, very interesting trade-off, or a risk trade-off that we need to incorporate into our regulatory standards.
Wow. Okay. So there's a little bit of guilt whenever we desalinize or desalinate. We're feeling a little bit guilty because we've just spent energy that is causing some other engineer some challenges. So do you work together, or is it the other guy's problem?
Yeah. So in the past, most of our water treatment regulatory standards have basically overlooked this externality associated with air emissions to achieve really high water quality. And, I'm a water treatment engineer. I love clean water. I want to go on the record as loving clean water. Okay.
Noted.
But I'm also very conscious that by far the largest sort of morbidity and mortality effects are associated with air emissions. And so one of the things that I've worked really hard to do is come up with sort of clear policy frameworks that help regulators bring the air emission externalities into their calculations when they're setting efficient standards for clean water.
So you have talked about in your writings, you've talked about moving towards the electrification of the water supply, either the linear one that you described to us, but I know that what you're thinking about is the circular one. What does the electrification of the water supply mean? And I know it's related to this air issue.
Yeah, so most of our water treatment processes, not so much desalination, but all the other water treatment processes are actually really chemically intensive. And that means that even as our grid decarbonizes or our energy sources get cleaner and cleaner, our water treatment externalities, or these air emissions from water treatment, aren't going to budge very much.
Okay.
So our SOx emissions, our NOx emissions, our PM 2.5 emissions, our carbon emissions aren't really.
I'm sorry, I have to stop you. SOx and NOx. It sounds like a child's
um,
book.
those, yeah, it's true, Dr. Seuss. I read a lot of Dr. Seuss to my 2-year-old son.
I suspect you do.
So these are air emissions that are commonly associated with coal and natural gas fired power generation.
Okay.
And have really substantive impacts on human health, primarily through respiratory and cardiac issues. So one of the things that we're trying to understand is how to more fully electrify water treatment trains so that as the grid gets cleaner, our water treatment systems also get cleaner. And that matters for kind of short-term public health gains.
Mm-hmm.
It also matters for long-term carbon emissions associated with our water treatment sector.
So can you it's not immediately obviously. So when you say we're chemically intensive right now, is that things like adding chlorine to the water? I mean,
Yes.
I hate to be so simplistic, but
no, great
show
questions.
me a couple of ways where these chemicals, we might not even realize the chemical intensivity, if that's a word, of the processes.
Yeah, so the first thing we want to do in most surface water, freshwater treatment is to remove small particles. So we add coagulants, and those are usually polymers or, there's a couple of different types of coagulants.
But these get things to stick together and fall to the bottom of the tank. To
stick together and to settle out.
Right.
We also want to remove hardness, so divalent ions like calcium and magnesium that cause scaling in your pipes.
Yes.
And so we often are softening our water.
Yes.
And we want to disinfect it, so we're adding chlorine. And all of these steps are basically the addition of chemicals that are manufactured off-site, primarily using thermal processes, often also incorporating mining operations and large-scale extraction operations. And so when you look at the whole life cycle of your water treatment system, it's big. It's really, really big.
Gotcha. That was really helpful.
It's pretty emissions intensive.
But the new insight that I've learned from you is that all that stuff that you just described, where chemicals are used, there is a chance that we'll be able to move some or all of those processes to be electricity based.
That's right. So instead of chemical coagulation, we might be able to use a process like electrocoagulation.
Okay.
Either by, so in electrocoagulation, you're generating those chemicals in situ, and you are doing so basically via the application of an electric field. Alternatively, we can think about true process substitution and eliminating chemicals altogether. So for instance, using membrane filtration in lieu of activated carbon removal of organics, or using nanofiltration in lieu of softening processes, chemical softening processes.
Right. So, okay. So that's really exciting because for all of these things, there's at least hope that we'll be able to, and I love the argument that you made, which is that the more we can move to electricity, then the water industry is on the back of the electrical industry. And if they get green, the water industry automatically gets green along with them, which is currently, as I understand it, not the case.
That's right. Now, there's a secondary benefit to all of this as well that I'd love to highlight.
Yeah.
And that is that as you electrify your unit processes, You also set up the opportunity for water treatment systems to provide demand response services for the electricity grid. So you could think about
I'm going to turn off my
ramping
phone.
and
Sorry about that.
trimming your water treatment production capacity in response to the availability of cheap electrons on the grid. And that would save money for water utilities, but it would also help to stabilize a much more um, renewable intensive, but maybe less reliable grid.
So that leads me to my final set of questions, which is, you have recently been involved in a big new Department of Energy center for research in all of these areas. And in fact, you're directing the research at this research center, which sounds to me like a pretty pivotal position. Tell me about the new center and why should we be all excited about it?
Yeah, so this is DOE's first big investment in water desalination technologies. And it is a DOE Energy Water Desalination Hub entitled the National Alliance for Water Innovation. We're based out of Lawrence Berkeley Lab, but we are really a partnership of over 50 national laboratories, universities, companies, et cetera. I think actually last week we hit 200 Alliance members. So it's really a national effort to help realize some of the technology innovation necessary for realizing these small scale desalination systems that are going to be so critical to enabling a circular water economy, but also sort of more generally innovating in spaces that are valuable to large scale centralized desalination facilities as well.
And it sounds like one of your tasks as a director of research is to figure out where to place the bets on the emerging technologies. That sounds like it might be fun.
Yeah, no, it's an amazing opportunity, and actually one in which I get to do a lot of interesting science. So one of the big questions that we've tackled in our lab is, what is the value of innovation? And this is actually a really challenging thing to get at, especially in systems where you have so many moving parts and pieces. And the performance of one component strongly influences the performance of another component, also the performance of the system as a whole.
Right.
So we've done a lot of work in developing new tools to understand where an innovation or a component advancement is likely to confer large cost and energy benefits in the desalination space, and in the process help guide our field away from kind of research dead ends and toward things that are going to make really big impacts in the near term.
So it sounds like you're shepherding the taxpayer dollar extremely
I'm,
well.
I'm doing my best.
Thank you for listening to The Future of Everything. I'm Russ Altman. If you missed any of this episode, listen anytime on demand with the SiriusXM app.